So welcome, I'm Catherine Pfaff. I'm a math professor at Queen's University in Kingston, Ontario. And this is another one of my lectures of giving kind of background material in different notation and skills and so on that can help you in when you're taking higher mathematics courses. So today I want to talk about the existential quantifier, which looks like a backwards E like this. And there's a reason for it because, so what does this mean? So this existential quantifier like this means anytime you see it in a statement, you can replace it with there exists. Okay, so let's do an example really quickly. So if I wrote there exists and x in the integers such that x squared plus 16 equals 25, okay? Then I could kind of break this down. So I'm just going to underline as I'm going to break it down like this. I'm going to break it down like this and this. And when I wrote it out, I could write, so what does this mean? This means there exists an integer x so that x squared plus 16 equals 25. Okay? So I can go through. So here's where my existential quantifier kicked in. So this was the existential quantifier that there exists and integer x. X is contained in the integers, so that's an integer x. And then this is just, we often do that shorthand for so that. So I kind of wanted to emphasize that too. Okay. So how do you prove or disprove a statement involving the existential quantifier? So let's talk about that for a second. So to prove and this is for a there exists statement, okay, the first thing that you should do is that you should state an example. And then you should show the example works. Right? In the sense that it satisfies all the desired properties. Okay, and I know we do not show in your final product prove how you found it. That's kind of a scratch work thing. You do that in private. Okay, so that's how we prove it. We state an example. So yeah, in your scratch work, you're going to need to find the example, and we'll kind of go through that. And then you need to show the example works in the sense it actually satisfies the properties you want. So in this case, right, we would need that it's an integer and that it satisfies this. Okay? So how do we disprove a there exists statement? So to disprove a there exists statement, what do? Okay, so I need to show, and this is where this gets a little bit trickier, so I need to show that no example satisfies all properties in this statement. Okay, and just as some kind of hint, often it works to do a proof by contradiction. Basically say, if there was an example satisfying this, and then you would get some implications that would contradict the properties. Okay, so sometimes we use a proof by contradiction for this. Okay. So to prove such a statement, you give an example, you show it works. To disprove it, that's trickier because you have to show there are no examples, and then often that's a proof by contradiction. Okay, which is the, it's a whole nother style of proof that hopefully at some point I'll make a video for. Okay, so let's do an example. So we're going to do a proof example. Of a there exists statement. Okay, so we're going to show there exists an integer x such that this. Okay, so the statement we had before. So let's kind of try to find, so we need to find an example. So we do this in our scratch work, we remember. So let's do some scratch work. So to indicate that something's scratch work, I kind of make squiggly lines around it. Okay, so here we go. So we're going to find an example by working backwards. This is one way to find an example. And I know that this is funny. We're going to find an example by example working backwards. But, you know, for example, working backwards. We're going to find an example, for example, by working backwards. Now I think I got all the words in the right place. Okay, so let's just start. So we're used to doing this kind of thing. We've done this our whole lives. We're just solving an equation. Okay, so I'm just going to go through this because I'm assuming by now that we're advanced enough that we can do this. Okay, we only need one of these. And so I'm going to choose 3. Okay, so let's check that it works. Okay, so what I'm going to do, so how do I check that it works? Well, I know that has to satisfy the equation, so I sub x equals 3 into x squared plus 16 equals 25, so let's go ahead and do that. So I get 3 squared plus 16. Hey, it's exactly what I wanted. I'm a happy camper. Always good to be a happy camper. Okay. I found an example. I showed it worked. Let's actually look at what our final product proof would look like. Okay, so for a final product, I'm going to make a really nice box, unlike my squiggle box. Okay, so claim there exists an integer x right? Satisfying. Then my equation was x squared plus 16 equals 25. So here we go. This is the proof of my claim. Let x equals 3. So this is my stating my example. Okay, then I have that 3 squared plus 16 equals 25 implies that x squared plus 16 equals 25 for x equals 3 as desired. And then we can either put a box or a QED depending on our mood. Okay, so I like to annotate things so that we can see in here what's going on. Okay, so this is our final product. It's a nice complete sentences. I didn't include any extra nonsense like how I actually got it. So this is the first part, right? This is where I stated the example. Right? And then in this part, actually I kind of do it there, right? I'm just showing it works. Now we could note, because I said x had to be an integer, it would be nice to actually note that 3 is indeed an integer. But otherwise, this is perfect, just like that. Okay. So I want to say a few more things about the existential quantifier now that you kind of understand how to prove things with it and so on. So, the existential quantifier can end up disguised in a statement. So there exists disguised in a statement. Okay, so some definitions involve sometimes disguised existential quantifiers. Okay, so here's a brilliant example of this. So definition. Maybe you've seen this definition before. So an even number is an integer of the form n equals 2k for some k in the integers. Okay, you're looking at that and you're saying, I don't see it. You said there's an existential quantifier, so it should be there exists. I don't see there exists. Okay? So where it's hidden actually is, here's its hidden form, okay? Right? This is where it's hidden. Okay? Because think about it like this. This could have been written in the form, or this could be written in the form. Right? There exists a k in the integers, right? Because this was for some k in the integers, this was like another way of saying there exists, right? Such that n equals 2k. Okay? So to prove a number, right? So to prove an integer is even, you need to find the k and show, right, this is where I was saying, in that case it was just kind of obvious, but to show that k is actually in the integers and n equals 2k. So why do I say you need to show it? Because sometimes when we're doing this, the number, we're not giving an explicit number like 3, which we happen to know is in the integers. And so you actually need to show whatever your k is, whatever crazy formula you have, that this is actually in the integers. Okay. So we also have some kinds of special versions of the existential quantifier. So here are our special versions. Okay, so if I write like this, right, this means there exists unique i.e. there exists precisely one. Okay, so how would you prove that? So to prove there exists a unique statement, okay, so what you need to do is, so the first part is the same as for a typical there exists proof. So you state an example. Okay, you show the example works. i.e. satisfies all these desired properties that you know, all your hopes and dreams of it. Okay, and then you show, so there's more than one way to do this, okay? If you already have existence, you can do uniqueness by showing that any two things satisfying all the desired properties have to be the same. But if you already have an example, it's often easier to show any example satisfying the desired properties is equal to your original example. Okay. So there's just this extra step where you show that any example satisfying that has to equal your original example, and you use the fact that it satisfies the properties also, and you end up getting that the two things are equal. Okay. So that's one kind of special version of there exists. Here's another one. So there exists, no, like this. Okay, so you've probably seen this before. We like to put a slash through something to like add no to it, to negate it. Okay, so this means there exists no. Okay, so proving a there exists no statement. I'm really sloppy in writing that, aren't I? There we go. Beautiful. Okay, there exists no statement is exactly the same as disproving a there exists statement. I.e., one usually uses a proof by contradiction. Okay. And I think that's enough for today. So thank you for learning with me today, and I hope that that's useful and helpful, and that you'll watch more of our videos in the future.